Thank you very much. Thank you very much to Al for the invitation. It's very nice to be here. And by here, I mean sitting in my own house, obviously. So I want to talk today about some joint work I did with a former student of mine, who's a guy called Alex Kite. And calling it joint work is slightly lying. I mean, basically, it's part of his thesis that I want to talk about. But unfortunately, he hasn't stayed in maths, so he's not giving talks about it. I mean, I say unfortunate. It's not unfortunate for him. He's very happy being a banker. But it's unfortunate for me because he was a very good mathematician. But so he's not going around giving talks about his thesis. So I thought it's reasonable if I do. So I've taken ownership of part of his work. And I gave a talk in the Cal seminar back in the autumn, which feels a very long time ago now. And there's a certain amount of overlap, but looking at the audience, I'm not sure there's much overlap in the audience, so maybe that doesn't matter very much. But if you were in that Cal seminar, then I'm going to talk about a slightly different aspect of what I talked about from then, but they do sort of go together nicely. So let me give you a little bit of an overview of what I'm planning to do in this talk. The structure of this talk, I really hate myself for doing this. Here's the structure of this talk. I'm going to tell you about a technical result that we proved. And then after I've told you the theorem, I'm going to tell you the motivation about why we proved that technical result. And I think this is absolutely horribly the wrong way around to do it. And I should have told you the motivation. First, the reason I'm not doing it that way is because explaining the motivation takes quite a long time. And I'm worried that if I do all of the motivation properly, I'll run out of time to tell you the result. That was one reason. And the other reason is that my Cal talk that I mentioned was almost entirely about the motivational picture. So I was sort of hoping that if people had been to that talk, they would know all the motivation already. So if you haven't, then I'm sorry. But hopefully I'll get through part one. So part one, I'm going to tell you about the theorem, and part two, I'm going to tell you about why I think it's more interesting. And hopefully we'll get through part one in good enough time that I can then explain all of the background that I want to. Right, so that's all my apologies and caveats out of the way, and maybe I can tell you what the talk is actually about. So part one is about a theorem that we have proved, which is about the derived category of coherent sheaves on a toric variety. So toric varieties are pretty straightforward, and it turns out their derived categories are in many ways fairly straightforward. One of the things you can do when you have a toric variety is decompose its derived category, produce things called semi-orthogonal decompositions, which I will explain a little bit more about. And this comes from the birational geometry. So you look at the other birational models of your toric variety, and that gives you a decomposition of the derived category. And the theorem that we proved that I will explain is that there is a Jordan-Holder result here, that when you do these decompositions, there are many choices you can make, but at the end of the day, the irreducible factors that you get are independent of the choices that you made, right? So it's just like decomposing a module into, writing down the composition series for a group or a module. It doesn't matter how you do it. At the end of the day, the list of the composition factors are the same. So that's our technical result. And then part two is to explain why this is interesting and why we proved it. And the reason is sort of physicsy. It's to do with autoequivalences acting on Calabi-Yau toric varieties. So if you have a Calabi-Yau toric variety, the story is a bit different. The derived category is not going to have any decompositions. That's impossible. Instead, what you'll have is lots of symmetries. So the same story with the birational geometry doesn't give you decompositions. It gives you autoequivalences, symmetries of the derived category. And it gives you a lot of them. So you get a big group of symmetries acting. And we want to know what is this group that's acting. And physics tells us it should be at the fundamental group of some space, some other space, which is called the Fi parameter space. And I will explain a bit more about this in part two. And the point is that in order for this picture to make sense, firstly, our Jordan-Holder property had to be true, which we proved it is true. And secondly, and this is the conjecture, the multiplicities of the irreducible factors that show up, those multiplicities have to agree with something in the geometry, right? So there's some intersection multiplicities that show up in the Fi parameter space, and there's some numbers there. Those numbers have to agree with our multiplicities of our irreducible factors. So that's our conjecture, and the conjecture is what I really think is interesting. The theorem is not particularly deep or interesting, but the conjecture I think is really is sort of worthwhile. Anyway, hopefully we'll get all of that in good time. Right, let me go to somewhere near the beginning of the subject and tell you what a semi-orthogonal decomposition is. So I'm talking here about the derived category of coherent sheaves on a variety X. And that is a category that's a triangulated category. And what we're interested in is ways of breaking that category up into smaller pieces to make it easier to understand. And the usual way of doing that is called a semi-orthogonal decomposition. So here's the definition. It's a sequence of subcategories which together generate the whole thing. And they're written in an ordered list, so C1 up to CR. And the semi-orthogonality bit is the statement that there are no morphisms in the backwards direction. So you can have morphisms from C1 to C2, but you cannot have any morphisms from C2 back to C1 again. So it's sort of an upper triangular thing, right? It's like saying you have an upper triangular matrix or a block upper triangular matrix. The C's are the blocks, and you only have morphisms in the top right corner, not in the bottom left-hand corner. And it's sort of analogous to having a semi-direct product of groups, I guess. So if you have a semi-orthogonal decomposition of your category, it gives you a certain amount of control of the category in terms of the smaller pieces. For example, the K-theory and the homology split up into, they just split as direct sums. They don't care that it's upper triangular. And then notationally, the standard notation for semi-orthogonal decompositions is with these angular brackets. Is my cursor visible as I'm sharing the screen?
Yes, I can see your cursor.
If I point at things on my slide, then it's visible to everybody. Yeah, so this is the standard notation with these angular brackets, the subcategories. In this talk, when I get a semi-orthogonal decomposition, the pieces, the subcategories that show up, these C's, they're always going to be equivalent to the derived category of some other variety, right? Some YIs. And for the purpose of this talk, I'm introducing a notational shorthand, which is I'm just going to write what I've written at the bottom here. dbx split up into the y1 up to the yrs. So y1 is a variety, but what I mean is the derived category of coherent sheaves on y1. This is not standard notation. I just invented it for this talk because I found all the slides were getting a bit hard to read, so I took out loads of db's and it seemed to work. So hopefully that's more helpful than it is confusing. We shall find out. Okay, so how could this possibly arise that you can decompose the derived category of X into the derived categories of some other varieties? Well, here is a classic example due to Orlov in the 90s, and it comes when you blow up, right? When you do a blow up, this happens. So let me take a threefold. So Y is a threefold, and I'm going to blow it up at a point and get a new threefold, which is X. Okay, so X is the blow up of Y. And so there's an exceptional divisor, which in this case is going to be a P2 because I blew up a threefold at a smooth point. So the exceptional divisor is a P2. Now, there is automatically a sheaf here, which is the skyscraper sheaf along this exceptional divisor. So that gives me an object in the derived category of X, blown up thing. And it's easy enough to calculate that that is what's called an exceptional object in the derived category, which means that its endomorphisms ring contains basically just the identity and nothing else. So the identity, scalar multiples of the identity. So it has no other automorphisms, no other endomorphisms, and no other higher derived endomorphisms either. So no x1s, no x2s, just the identity. And what that means is that if you look at the subcategory generated by this object, by this sheaf, there's basically nothing you can do, right? Because when you generate a subcategory, you like you take direct sums, you take mapping cones, but there are no morphisms to play with because there is only the identity morphism. So all you can do is take this object and direct sums of this object with itself. And that is all you will get. So if you think about it, the subcategory that you generate, starting with OE, is a very simple thing. And it's just equivalent to the derived category of a point. Or if you like, the derived category of vector spaces. That's what this category looks like. Now, it's a pretty straightforward thing to prove, and as I say, this is Orlov's observation, that the derived category of the blown up threefold has a semi-orthogonal decomposition into three pieces. The first piece is the thing you started with, the threefold before you blew up, and then there are two copies of the derived category of a point. And those two subcategories, those points there, are generated by exceptional objects, and they are basically this OE, the skyscraper sheaf along OE. So actually what you do is you take OE and then you twist it by two different line bundles, and then you get those things are still exceptional objects. So you actually have a whole bunch of exceptional objects, and you just pick the right two of them, and you get this semi-orthogonal decomposition. Okay, so in some sort of categorical sense, you can think that X has been built out of Y and 2 points. Okay, that's what its derived category looks like. Okay, so how does this generalize? So here is Orlov's blow-up formula, which is a very nice observation, but it's not particularly difficult to prove. If you take any variety and you blow it up in a smooth subvariety, then the derived category of the blown up space has a semi-orthogonal decomposition into the thing you started with, and then a bunch of copies of the thing you blew up. And the number of copies is one less than the codimension of what you blew up. So on the previous slide, I blew up a point in a threefold, so that was codimension 3, so I got 2 copies of the point. Okay? So this is Orlov's blow-up formula. It's quite a famous result. I'm sure most of you, or many of you, have heard of it before. So when we do blow-ups, you get semi-orthogonal decompositions. Great, but what is a blow-up, right? It's just an example of a birational transformation. It's the simplest kind of birational transformation. So what about other kinds of birational transformations? So there is a sort of rather vague meta-conjecture that birational transformations will lead you to semi-orthogonal decompositions. There is no general theorem here. It's more just of a research area. There's lots of active work on these things and different kinds of birational transformations. But what I want to tell you about is a particular kind of birational transformation, which is quite easy to understand, where we do understand what's going on with the derived categories and we see the semi-orthogonal decompositions. And the class of birational transformations I want to talk about arise from a variation of GIT quotients with abelian quotient groups. So abelian VGIT. So let me give you an example to explain what I mean by these words. Let us take C4 and act on it with C star, which is of course an abelian group. And instead of just acting with the usual diagonal action, I'm going to act with the weights I've written here. So 1, 1, 1, and -1. Now, this is what I would call a GIT problem. So I have a space C4 with a group acting on it, and now I want to take quotients. And I want them to be nice. I'm going to take GIT quotients. And there are two possibilities. There are two different GIT quotients you could take, because a GIT quotient depends on the choice of character, and C star has, basically 2 characters, as the positive characters and negative characters. And if you take the positive characters, then the quotient you get is this space X plus. And what this notation means is it's the total space of the O-1 line bundle over P2. So hopefully that's clear, right? The first 3 coordinates give you the P2, and then the last coordinate gives you the fiber, the O-1 fiber. The other possible quotient, if you take the negative character, is much simpler. It's just A3, okay? Because the last coordinate just becomes non-zero, and you can scale it away, and you're left with A3. Okay, so you have 2 different GIT quotients. Now, whenever you have 2 different GIT quotients, they're going to be birational, right? Assuming one of them is non-empty or something. So this is a kind of birational transformation coming from variation of GIT. And in this particular example, it's just a blow up, right? It's just a special case of my previous example. I took A3 and I blew up the origin, and that gives you, that's what X plus is. X plus is the blow up of A3 at the origin. Okay, so you know immediately from my Orlov's blow-up formula that you have this semi-orthogonal decomposition. X plus decomposes into X minus and 2 copies of a point. I want to do a slight psychological change here. In my previous slide, when I blew up a point, and then I got the derived category decomposing into something plus a point, you probably thought that the points you saw in this decomposition, that's the point I blew up, right? That's why it's a point. And when I blew up a Z, I got a Z, right? And you're absolutely correct. That is where it came from. But when you're doing VGIT, that's actually not the right way to think about it. The point in this decomposition, the point, you should think of that as the origin in C4, right? The point is that in C4, there is a unique fixed point, which is the origin, and that is the point that's showing up in this semi-orthogonal decomposition. It's not the origin in A3, because the origin in C4 is unstable with respect to both characters, so it doesn't go to the origin in A3. Okay, so what's the significance of that? Well, let me change my numbers a little bit. Okay, so let me add 2 more weights. So let me make it now 4 copies of 1 and 2 copies of -1. So I'm acting on C6. So how does that change the story? Well, the two GIT quotients change. So the first one is now a vector bundle over P3. So the first 4 coordinates give me P3, and then the other 2 give me 2 copies of the O-1 line bundle. So this is a rank 2 vector bundle over P3. And the other quotient is a rank 4 vector bundle over P1. Okay. So this is a birational transformation between X plus and X minus, but it's not a blow up anymore. I would call it a flip. It's possible I'm abusing the word flip if I call it a flip, but that is what I would call it. So what's happening is you're contracting the P3 and then you're gluing in a P1 or vice versa. So the point is that this semi-orthogonal decomposition still holds, right? Just as it did before. And now, you know, there is no, you didn't do a blow up in a point. There is no point in X minus for that point to be significant. So the point really is now just the origin in C6. Geometrically, that's where it came from. So it's easy enough to prove this, right? These are very simple spaces. You can do explicit calculations and just prove that this decomposition holds. And one numerical observation, why are there exactly 2 points? And the reason there's 2 is because that's the sum of the weights. If I add up, you know, all the weights, I get 4 minus 2 is 2, so there is 2 points. So if I added on 1 more copy of 1 more positive weight, then I'd get 3 points. Okay. So this is easy enough to prove by direct calculation, but there is a general theorem here, proven by various people, and it sort of says this generalizes to whenever you have a C star VGIT. Right, so you have you're doing 2 different GIT quotients, and the group you're quotienting by is C star. So here's the statement of the theorem. So I take any variety U with an action of C star on it. I look at the fixed locus, that's Z, and let me assume the fixed locus is connected. That simplifies things quite a lot because it means that the wall crossing can only be something rather straightforward. And here's a numerical condition. I want to look at the normal bundle to the fixed locus and take its determinant, and then that has some weight under the C star action, and that weight I'm calling kappa. I'm going to assume that weight is positive. So that kappa, by the way, on the previous slide, that kappa is the sum of the weights, right? The fixed locus in this example is the origin. The normal bundle is just C6 again, and it's the weight of its determinant is 2, because that's the sum of the weights. Okay, so the sum of the weights here is that's what it's turning into kappa on this page. So assuming kappa is positive, then the derived category of X plus splits up as a semi-orthogonal decomposition into X minus, the other. So I've got two GIT quotients, right? I've got x plus and x minus, and x plus splits up into x minus plus a number of copies of z, where z is the fixed locus. Okay, and the number of copies is kappa. So this condition that kappa was positive is not a restriction at all, right? If kappa is negative, you just swap the roles of x plus and x minus. Okay, it's just kappa being positive just tells me which side is x plus and which side is x minus. That's not a really restriction. Okay, so I think this is a very nice theorem. It implies Orlov's blow-up formula. You can see formally it's very similar. So any blow-up can be constructed as a C star VGIT. So you can just apply this theorem and get Orlov's formula out immediately. Another thing to observe is that it's possible that x minus is empty, right? So one example you might think of is to construct projective space. So you would just take c to the n plus 1 and act by c star just diagonally. And then there are two GIT quotients, but one of them is empty. But that's fine. The theorem still applies, but it just tells you that the derived category of Pn splits up into a number of copies of points, right? Because there is no x minus contribution. And what are those points? Well, they have to be exceptional objects in the derived category, right? So what this is saying is that Pn, derived category of Pn, has a full exceptional collection. It has a bunch of exceptional objects which generate the entire category. Now that is another extremely well-known result that was proved by Sasha Bailenson long ago, and it's just the exceptional objects are just a list of line bundles. It's very straightforward. So as I say, this is a nice theorem because you can immediately prove two very classical results in derived categories straight from it. One last observation, which will be important in part 2 of the talk, is what happens if kappa is 0. So if kappa is 0, then you get no copies of z, and the theorem tells you that x plus and x minus are derived equivalent. They have the same derived category. Okay, and that is a situation I would call a flop. Right, when kappa is 0, the two sides are derived equivalent. But we'll come back to that later. Okay, right. Let me take this theorem and apply it to something. Learning things about the derived categories of toric varieties. Okay, so when I say toric variety, I don't quite mean any toric variety. What I want to do is take a vector space and quotient it by an action of a torus. So C star to the R is going to act on a vector space. And this is a GIT problem. So you want to look at the different possible GIT quotients you could get, V / the torus. Every one of these GIT quotients is a toric variety. Now, it's not quite true that every toric variety arises in this way as a quotient of a vector space by a torus, but it's kind of approximately true. I mean, most toric varieties in practice that you're interested in do arise in this way. A stupid piece of terminology, the different GIT quotients I'm going to probably call phases, just because I read too much physics, probably. So when I say phase, I just mean the different GIT quotients. So I have all these toric varieties, and they're all birational, right? They're all just different GIT quotients of the same thing. So they're all birational. And if you've ever seen, if you've ever seen GIT before, you probably know what the secondary fan is. If you haven't seen GIT before, you will have no idea what I'm talking about. So it's probably irrelevant. So let me just remind you, the space of characters, so those are the stability conditions for GIT, it has a wall and chamber structure, which is called the secondary fan. So the chambers are the characters which all give the same GIT quotient, and then you cross through a wall and the GIT quotient changes and you get a birational transformation. And yeah, that structure, that splitting up of the space of characters is called the secondary fan. Something to note is that when you do a single wall crossing, so you go from one chamber to an adjacent chamber through a codimension 1 wall, you can think of that as a VGIT, but not for the rank R torus, but just for the group C star. So what you do is you take a character that lives exactly on the wall, and that will then destabilize a bunch of stuff. So you throw away everything that's unstable for that guy, and that will leave you some subset U. And now you just have a remaining copy of C star going on. So orthogonal to the wall is a copy of C star, and that C star controls this wall crossing. And xi and xj are the two possible quotients of U by C star. Okay? So when you have a single wall crossing, you can think that the group is just C star, and you can apply the theorem from the previous slide. So that theorem told you that when you cross the wall, you get a semi-orthogonal decomposition, right? One side of the wall can be decomposed into a copy of the other side plus a bunch of copies of the fixed locus, okay? And if you want to make your category, if you want to decompose your category, what you do is you cross through a wall, making sure that kappa has the right sign, right? Some walls kappa will be positive, some walls kappa will be negative. So you start with your phase that you want to decompose, you cross through a wall where kappa is negative or something, and then your category decomposes into a new phase and some other pieces, and then you do it again, right? You cross through another wall where kappa has the right sign, and then the category decomposes again, and you keep going until you get to kind of a minimal phase, which can't be decomposed any further, right? So there will be a phase where all the wall crossings are in the wrong direction, and you can't decompose that thing any smaller. Okay, and that's how you do it. That's how you decompose your derived category of a toric variety into simpler pieces. Maybe one thing to note that maybe when I say toric variety, some of you might be thinking about compact toric varieties like projective space or something, which is reasonable. So projective space, of course, decomposes into exceptional objects, as I showed you on the previous slide. You can see from this process that if you start with any compact toric variety and you apply this process, you're going to end up with just an exceptional collection. It's going to decompose into copies of the point and nothing else. That's all the pieces. So this procedure implies that any compact toric variety has a full exceptional collection. But really my interest is in non-compact toric varieties for this talk, and then you don't get an exceptional collection. You get some points, but you also get some bigger pieces as well. Okay, let me do an example. Now, there's some toric calculations, some GIT calculations in this example. I am not expecting anyone to follow the calculations in real time, unless you're, a really hardcore toric nerd. But I'm going to run through the example very quickly. It doesn't matter about the details. I just want to give you a flavor of something so that I can explain what my theorem is. Okay, so here's my example. I'm taking C6 and I'm acting on it with a rank 2 torus with a particular matrix of weights, which is written down here. And I claim that the secondary fan for this problem is what's drawn above. So there are 4 possible phases, 4 GIT quotients of C6 by this action of C star squared. And the simplest one is in the one I've labeled phase 1. It's just a copy of A4. And the most complicated one is something I've called X in phase 4. And it doesn't matter what it is. It's a total space of a line bundle over some compact threefold, which is itself a projective bundle over P1. But it's not important. Okay, so the aim of the game is to decompose the derived category of X by passing through walls and making it split up using our theorem, not our theorem, the theorem from a few slides ago. Okay, so let's do it. So what do these wall crossings look like? So the first wall crossing I'm going to look at is from phase 1 to phase 2. So if you look at what's drawn in phase 2, you can see that phase 2 is actually the blow up of phase 1 at the origin. Right, so this wall crossing from 1 to 2 is just a blow up. Okay, so you get this decomposition of phase 2 in terms of a copy of A4 and 3 points, because I blew up a codimension 4 point. Okay, now let's keep going. Let's go from phase 2 to phase 4, and again this is a blow up, but not of a point. It's a blow up of a codimension 2 subvariety, which you get by taking a P1 in P3 and taking the line bundle over that guy. And this wall crossing blows up that entire subvariety. So you get a decomposition of phase 4 into phase 2, the line bundle on P3, and one copy of the thing you blew up. The thing you blew up was this surface. So you've got this fourfold and a surface in your decomposition. Now, of course, phase 2 we just noticed could be decomposed into phase 1. So I can do a further refinement, right? So X splits up into these 4 pieces. So one copy of phase 1, and then 4 other pieces, which are the things that you blow up, right? I blow up a point, I get 3 copies of a point, and then I blow up this surface, and I get a copy of that surface. Okay, so I get this decomposition of the derived category of X. Great. What happens if I go the other way? What if instead of going through phase 2, I go through phase 3? Let's look at those guys. So 1 to 3, this wall crossing again is a blow up. Okay, so the reason all of these wall crossings are blow ups is because I engineered the example to make all the wall crossings blow ups. They don't need to be. I just thought it was slightly simpler to talk about that. Okay, so 1 to 3 again happens by my design to be a blow up, but not a blow up of a point, a blow up of A2. Okay. So you blow up A2, and that tells you that phase 3 decomposes into one copy of A4 and one copy of A2. Okay. Now, the wall crossing from 3 to 4, again, is a blow up, and it blows up the P1. Right. If you look at what phase 3 is, you can see there's a P1 sitting in there in the origin, and I blow that up. That's codimension 3. So you get that phase 4 has a copy of phase 3 and 2 copies of P1. And if I combine that with the decomposition of phase 3, I get this decomposition. So the derived category of X has A4, A2, and 2 copies of P1. Okay, great. Let me summarize that. Well, you can think about this direction in 2 directions. You think you can go from 1 to 2 to 4, or maybe it's better to think that you start in 4. So you want to decompose phase 4, so you pass to phase 2, and then you pass to phase 1. And you get this decomposition, A4, 3 points, and this surface. Or you go to 3 and then to 1, and you get A4 and A2 and 2 copies of P1. Great. So you get 2 possible semi-orthogonal decompositions, and they look superficially kind of different. But now we say, hang on, we haven't really finished our game yet, because this surface and this P1, they are themselves toric varieties, right? And of course they're toric varieties. They have to be. How did I get them? I took the fixed locus of my C star, of one copy of C star inside my toric variety. So I will always get a toric variety if I'm doing this story. So I will always be able to decompose these pieces into smaller pieces. So how do they split up? Well, O minus 1 over P1, that's the blow up of the plane. So it splits up into a copy of A2 and a point. And P1 splits up into 2 points because it's got an exceptional collection. So if I do that further refinement, I end up with these 2 semi-orthogonal decompositions. Okay, and now they look a bit more similar, right? Each way, I got an A4, an A2, and 4 points. They're not the same decomposition because the order of the factors is different. They're related to each other by mutations, if you know what that means. But the point is that you can see that there is a Jordan-Holder property going on here. I did 2 really quite different choices, and I ended up with different decompositions. But at the end of the day, the factors that I got were the same. Okay? So there's the Jordan-Holder property in action, and here's our theorem, Alex and myself. When you do these semi-orthogonal decompositions of the derived category of a toric variety, you will see this Jordan-Holder property. The pieces that you end up with at the end of the day, and the number of each piece, the multiplicity of each irreducible factor, is independent of how you did it. So which phases you went through to do the decomposition, which paths you took in the secondary fan. So what can I say about this proof? It's not a particularly deep theorem. It's not very hard to prove. It's a pretty straightforward recursive thing. You'd get it down to the rank 2 case and then by some recursive procedure, and then you prove the rank 2 case. one thing to note why I say it's recursive. So in the example I just showed you, it was sort of, there were two steps, right? The first step was I passed from phase 4 to phase 1 by some choice of path, and I got a certain decomposition. And then the second step was to say, actually, some of these pieces are toric varieties and they can be decomposed. But the reason it took 2 steps instead of more is because it was a rank 2 torus which was acting. If it was a rank 3 torus, at this point in the story, the pieces I'd have, these blue pieces, they would still be decomposable, right? Because they would be built by some rank 1 GIT problem, and so they would still have decompositions. So in general, if you take C star to the n, you quotient by a rank R torus, then the algorithm is going to go to depth R. Okay, so you know it can be sort of complicated, but it's pretty easy to set up a recursive proof. Yeah, and one thing to note is this is not a formal property of semi-orthogonal decompositions. The Jordan-Holder property is not true in general. Semi-orthogonal decompositions, they're just not that nicely behaved. So there are lots of counterexamples. So this is very much a special feature of these semi-orthogonal decompositions produced in this algorithmic way. Okay, great. I managed to state the theorem. Oh, I still have like at least 20 minutes left. What time did we start? 30:30, 25 to?
Like 35, yeah, 33.
Excellent. Yeah. Lovely. Great. Okay. Cool. So I have time to tell you why we proved this theorem, because I don't think it's a particularly exciting theorem, but I do quite like the motivation. So let me move on and tell you about the why. Maybe this is a good point to pause. Did anyone have any questions at this moment? No? Nothing appearing in the chat? Everybody's content. Great, let's plow on. Okay, so what I'm really interested in is Calabi-Yau toric varieties. So a Calabi-Yau toric variety is never going to be compact. Okay, it's always going to be non-compact. But the derived categories of Calabi-Yaus never admit semi-orthogonal decompositions. It's just not compatible with stair duality. So that is not what happens. So what does happen? Well, let me first of all state a general result rather than something for toric varieties. So let me suppose I have C star acting on some variety U, and I make the same assumption before, which is the fixed locus is connected. But now let's focus on the case that kappa equals 0. Okay, so the sum of the weights is 0. Then, as I pointed out, what that earlier theorem told you was that the derived category of x plus is the same as the derived category of x minus, right? Because in that semi-orthogonal decomposition, you see 0 extra copies of z. So the derived categories have to be the same. Okay? So this is a birational transformation where you get not a semi-orthogonal decomposition, but a derived equivalence. Okay? And it's a K equivalence, if you like, or a flop. What's happening is the canonical bundle is not changing, right? So it is a sort of Calabi-Yau style situation, right? For example, both x plus and x minus could have trivial canonical bundles. They could both be Calabi-Yaus. That would be the sort of thing that would happen. So fine. So the derived categories are the same. That's nice. But what's even more important to realize is that they're not canonically the same. The theory which produces that earlier theorem doesn't give you a single derived equivalence. It gives you a whole countable family of derived equivalences, which I'm going to call phi k. So it's indexed by the integers, different possible derived equivalences from one to the other, which means immediately you get symmetries. You get auto-equivalences of x plus. Because what you can do is you can use phi 0 to go from left to right, and then you can use phi 1 inverse to come back again, right? And that will not be the identity on dbx plus. It will be a non-trivial autoequivalence, a symmetry of this derived category. Okay? And there's a theorem here which I'm going to attribute to Happen, Leistner, Shipman. It sort of goes back a bit earlier than them, but they definitely wrote up one proof of it, which tells you kind of what this symmetry is. And what it is, it's the twist around a certain spherical functor coming from the derived category of Z, the fixed locus again. Now, if you don't know what spherical functors are, I'm afraid I'm not going to tell you what they are in this talk. So if you do know, that's great. But if you don't, all you need to take from this theorem is, OK, so in the semi-orthogonal decomposition case, when kappa was positive, you saw Z appearing, right? Z showed up in the semi-orthogonal decomposition some number of times. In the kappa equals 0 case, there is no semi-orthogonal decomposition, but Z is still very important. So Z is now controlling the symmetry that you get. This autoequivalence is in some sense controlled by Z. Right? That's what you should read this as if you don't know what a spherical functor is. Z is controlling the symmetry. And one important fact is, if for some reason the derived category of Z has a semi-orthogonal decomposition, right? Z, of course, is a different variety from, it doesn't need to be Calabi-Yau. Z is some other thing. If Z has a semi-orthogonal decomposition, what that means is that this autoequivalence can be factored into simpler autoequivalences, according to the pieces that you split Z up into. Okay, so a semi-orthogonal decomposition of Z is telling you that this symmetry that you've just produced can be factored into smaller pieces, right? And that is a crucial point.
Sorry, Ed. But
hello.
Shouldn't there, this is Tim speaking, shouldn't there be some condition in the semi-orthogonal decomposition? Or are you saying that every time you decompose the base category of a spherical functor, you can factor the twist?
No, there's a condition which I've forgotten, which is something like the Serre functor has to preserve the pieces or something. It's ignoring it because it's automatically satisfied in the condition that I care, in the situation that I care about.
Oh, cool, thank you.
Great. Now, let's, with that theorem in mind, think about what happens if you have a Calabi-Yau toric variety. Okay. So, again, when I say toric variety, I mean I take a vector space and I want a quotient by a torus to get myself a toric variety. If I make the torus act through SLV, so everything is acting with trivial determinant. Any one parameter subgroup is acting such that the sum of the weights is 0. Then all the phases, all the GIT quotients will be Calabi-Yau. They'll all have trivial canonical bundle. And by our previous theorem, that means that all the phases are derived equivalent. Right? You have all these different Calabi-Yau varieties, and they're all birational to each other. They're all related by C star VGIT, so they're all derived equivalent. Okay, so every phase is derived equivalent. And more than that, as I was stressing on the previous slide, they're not derived equivalent in a canonical way. Every time you cross a wall, you have a whole bunch of different derived equivalencies you could choose, and that means you have a load of symmetries of each phase, right? And basically, the number of symmetries gets massive because you can cross to another phase and then do an autoequivalence through some other wall and then come back again, and that will give you a new autoequivalence to your original phase, right? So you can go to all your neighboring phases, and that produces loads of symmetries, but then you can go on to other phases and do more and more wall crossings. So you basically, when you have a toric Calabi-Yau, the autoequivalence group of its derived category is going to be pretty big, right? And this is the group that I'm interested in understanding. And physics hands us a prediction about what this group ought to be. It should be the fundamental group of something called the Fayet-Iliopoulos parameter space. I think in my cow talk, I went into a bit more detail about why this prediction is there, but I think for this talk, I'm just going to leave it hanging there. There is some space which comes to you from mirror symmetry, if you like, or it doesn't technically need mirror symmetry, but mirror symmetry is maybe a good way of thinking about it. And its fundamental group is supposed to be acting on the derived category of any one phase. So the sort of picture you should be having is that moving around between the different phases, in some physicsy sense, is moving in some associated parameter space. It's approximately the stringy version of the Kähler moduli space, the complexified Kähler moduli space of the phase. So you move around in this Kähler moduli space, you get to these different birational models, and you get some sort of monodromy action when you do that. So the fundamental group of this parameter space acts on the derived categories. So it's a sort of physical heuristic, but there is actually a completely precise definition of this Fi parameter space. It's the base of the Horry-Waffer mirror. It's the complex moduli space of the mirror. So it's the thing that shows up. It's the complement of the GKZ discriminant locus. So let me tell you a bit more about what this Fi parameter space is. Yeah. So maybe just to underline that moral point there, there's a physical heuristic which is not at all well defined, but the thing that is well defined is what this space is. Right? The Fi parameter space is something that's completely well defined, and its fundamental group is completely well defined. So this conjecture is very precise, right? This group should act on this category. The reason it should act is total physics of voodoo, but there is a very precise prediction here. Okay, so let me tell you what this Fi parameter space is, and it's all wrapped up in this dual toric variety. So I have a toric variety built by quotienting a vector space by a torus, and there's a secondary fan which controls all the different phases, and that you can just read that fan as defining a toric variety if you like, and that's called the dual, the Gale dual toric variety, this X check. And for Calabi-Yaus, this dual toric variety will be a compact toric variety. Okay, so what's the relationship between the geometry of the dual toric variety and the original side that we cared about? Well, chambers in the secondary fan, they correspond to phases of our original problem, and chambers in the secondary fan are the toric fixed points in X check. Okay, so you have a bunch of points in X check which correspond to our different phases. When I cross a wall, so that's a codimension 1 part of the fan for X check. So that means it's a rational curve in X check. So it's a torus invariant rational curve connecting two of the fixed points. So the phases correspond to fixed points in X check, and when I cross a wall, there's a particular P1 in X check which connects me from one phase to another phase. Okay. Now, of course, this X check does not have an interesting fundamental group. So to get the Fi parameter space, you have to cut a bunch of stuff out, and that's why you get an interesting fundamental group. So here's what you want to chop out. You want to throw away, first of all, throw away the entire toric boundary, which sounds a bit stupid, right? Because then you're just left with a torus, but it's much better to think of it that way. If I just start with a torus, it's very confusing. But if you start with X check and then throw away the boundary, it makes more sense. So that's easy. And then the hard bit, the bit that makes the story really difficult, is you also have to throw away something called the discriminant locus, so the GKZ discriminant locus. So this has an interpretation in mirror symmetry. So the mirror family lives over X check, and it will become degenerate over some locus, and that is the discriminant locus. And that's the thing that was studied by GKZ. So it's a hypersurface in X check. It's not toric. And it typically has multiple irreducible components. Okay, and understanding the geometry of this discriminant locus is really quite challenging. It's definitely the hardest part of the whole story. I mean, one point is, if you take a variety and you cut out a hypersurface, it's really hard to compute the fundamental group of what's left. It's a really challenging problem, and that is why I can't prove the prediction yet about the action of the fundamental group, simply because I cannot compute the fundamental group, because the topological question is too hard for me anyway. Alex was much better at it than me. So I'm sure there are people who are better at it than me. I should make contact with them. Okay, let me draw you a picture. Okay, so here are two pictures of the same thing. So what's going on the left here? So this is a picture of the FI parameter space. So I have 2 points, which are the intersections of these black lines, and those are my fixed points. And that's that point at the top is where the phase x1 corresponds to, and at the bottom you have the phase x2. So the black lines are meant to be the toric rational curves. And then I've drawn some of the discriminant as well. So the discriminant is some non-toric thing. And I've drawn 2 components, a red component and a blue component. Now, this line that goes from x1 to x2, of course, it's really a P1, a rational curve. So on the right-hand side, what I've done is I've drawn that rational curve as a 2-sphere, right? So what's going on with these missing points? So roughly what I want to do is I want to start at the point x1 and I want to do a loop, right? An element of the fundamental group. So I want to do a loop which takes me down towards x2 and then turns around and loops and comes back up again. Okay? Now, if I was literally the toric P1, the thing which is the black line, the thing which I've labeled C12, if I was literally that toric rational curve, I would see one missing point. The discriminant would intersect my rational curve in 1 point. So I have to delete that discriminant locus. So I take away that one single point, and then I would have a loop which went from the top of this 2-sphere, it went down around that missing point, and then it came back up again to the top. Okay? And that loop, I claim, is supposed to be the autoequivalence, which I discussed on earlier slides, the thing you get from wall crossing from the phase x1 to the phase x2 and back again. Right, the spherical twist around dBz. That is what that loop is supposed to do. But the key point is that when I form the FI parameter space, I actually have to throw away the toric boundary. So this toric rational curve that I'm staring at is not actually in my FI parameter space. It's been thrown away. So I'm not allowed to do that. I have to move a little bit off that rational curve. I'm going to perturb this black line a little bit to the left to make sure I'm actually in the FI parameter space and I haven't been thrown away. And when you move to the left, this single point of intersection with the discriminant splits up into multiple points. Okay? So every component of the discriminant which hits this point, it has some intersection multiplicity, and you will split up into that many points. So in the picture I've drawn, you can see there are 1 blue point, because the component delta 1 just intersected transversely. But there are 2 red points because the component delta 0, it intersected with intersection multiplicity 2. Okay? So when you perturb off, you see this splitting up of 1 intersection point into several intersection points. Okay? And the important thing is to know which components of the discriminant hit my C and what is their intersection multiplicity. Okay, and in terms of the fundamental group, of course, this is telling you that this loop I was interested in has factored into smaller loops. So I had a loop which started at x1, went all the way down to x2 and came back up again. And you can see instead of encircling a single point, it's really encircling 3 points, which means that it's really, you could factor it into 3 simpler loops. Okay? So that loop was supposed to correspond to a certain symmetry of the derived category of x1, and I claimed it was a symmetry controlled by a spherical functor starting at dBz. Okay, and that picture I just drew you of the FI parameter space is telling me that that symmetry ought to split up into simpler symmetries. And how could that be possible? Well, it would happen if the derived category of Z had a semi-orthogonal decomposition. Okay, So the fact that that single point split up into 3 separate points is strongly suggesting that the derived category of Z ought to have a semi-orthogonal decomposition into 3 pieces. Okay? So does it? Well, yes, it does, because Z is a toric variety. Okay, what was Z? It was the fixed locus of something. I had a Calabi-Yau toric variety, and I did a wall crossing, and I looked at the fixed locus for a particular one parameter subgroup. That will always give me a toric variety, and normally it won't be a Calabi-Yau. The ambient space is Calabi-Yau. There's no reason for the fixed locus to be Calabi-Yau. So it has a semi-orthogonal decomposition, as we were discussing in part 1. Right? It can be split up into lots of smaller pieces by doing wall crossing for Z. And the key observation, which is not at all deep, but it's not immediately obvious, but it's not hard to prove, is that if you stare at this decomposition of dvz and you ask yourself, well, okay, what possible factors could show up? Like in terms of the commoner torics, in terms of just the toric data and the weight matrix, you ask what are the possible irreducible components that could show up in dbz? It turns out that that set of potential irreducible components is exactly the same set which indexes the components of the discriminant. Okay, so just for combinatorial reasons, each of these components, this blue component or this red component, you can think of them as indexing categories which could potentially show up in dbz. Right? That's the idea. But we don't actually know that they do show up in dbz, and we don't know what multiplicity they show up with. Maybe there's 4 of them. So in this picture, you'd hope that dbz contains exactly 1 copy of the category associated to delta 1 and 2 copies of the category associated to delta 0. That's what you would hope. But we don't know if that's true. So that is our conjecture, that the multiplicity of each component in the semi-orthogonal decomposition of Z is precisely the intersection multiplicity of the curve with that component of the discriminant. So it's our conjecture, and it's sort of based on a physics paper written by Aspinwall-Plesser-Wang. It's not a particularly physicsy physics paper. I don't want to overstate how much work we had to do. I mean, Aspinwall knows as much maths as I do. So there's lots of maths in that paper, and they make some very precise discussions about what the categories are supposed to be and things. What we did is we looked at their work. We some of what they say was already a theorem, was already known. So we sort of honed in on which bits of their story are not actually proven yet, and we've managed to sort of make it a more precise conjecture. And the point of our earlier theorem about the Jordan-Holder property is that it makes this conjecture make sense. If the Jordan-Holder property wasn't true, then it wouldn't make sense to say the multiplicity of a component, because it wouldn't be a well-defined thing. So the purpose of the theorem is to make the conjecture well-defined. There is a well-defined multiplicity of each component. And then the hard part is the claim that it agrees with this geometric thing, which is the intersection multiplicity of the discriminant in the discriminant with the curve. And Alex proved that this conjecture always holds in the rank 2 case. So if the torus you were questioning by had rank 2, which is the same statement that the Fi parameter space is 2-dimensional. So the dual toric variety is 2-dimensional. So in that situation, the conjecture will always hold. The rank 1 case, it's completely vacuous. So rank 2 is the first case where something can show up, and Alex proved it. It's hard to get to rank 3, and I can tell you exactly what the problem is. The problem is the geometry of the discriminant gets more difficult. So there is a thing called Horn uniformization, which gives you a sort of rational parameterization of the discriminant, and in dimension 2 it's actually a morphism, and you can use it to compute intersection multiplicities. As soon as you get to dimension 3, it's only rational, and in order to compute the intersection multiplicities, you'd actually have to do some birational modifications to figure it out, and we just lost control of the geometry. So, as I say, there's no problem with the category theory. All of the difficulty is literally the algebraic geometry of the discriminant. Okay, great. I think I'm going to stop. Thank you.